Hi, my name is Scott Briggs, and I'm the team president of the Michigan Mars Rover team, also known as Rover. We're a student-run engineering team here at the University of Michigan, and over the last 6 months, we've been working hard to design, build, and test a rover fit to compete in the 2016 University Rover Challenge. This year's rover features many design innovations from both the mechanical and electrical teams.
The mechanical sub-team is responsible for the design and fabrication of the chassis, suspension, wheels, robotic arm, and soil collection system. To aid in the design and analysis of our chassis and suspension, we performed a drop test using a rover from a previous year which featured similar construction. From this testing, we were able to estimate the contact time, and from this, estimate the forces acting on the chassis and suspension. We used this as an input to our FEA, which allowed us to identify weak points in the chassis and suspension. The tested chassis failed due to stress concentrations at holes through the carbon fiber tube at the suspension connection joint. To compensate for this, we've redesigned the chassis to suspension joint to remove the holes through the carbon fiber tube. This year's suspension is a rocker bogie design, which is a passive suspension system which ensures a neutral chassis angle as well as contact between all 6 wheels and the ground. In addition, we've implemented a mechanical hard stop to prevent bogie inversion, which is an identified issue based on testing from last year's rover as well as in relevant academic literature. The rover wheels are entirely custom manufactured, and they feature in-hub motors, which significantly increases our ground clearance.
To accommodate a larger chassis, the increased size of our robotic arm required us to reevaluate our chosen materials in order to reduce its weight as much as possible and decrease the loads on each joint of the arm. Using material selection software, we were able to compare different materials' properties with their density in order to optimize our chosen materials. This was especially true in the hand, where the reduced mass was most important due to the increased moment arm. Specifically in the grippers of the hand, this analysis showed us that a nylon-based plastic would be most suitable for our needs. Producing these parts using stereolithography, an additive manufacturing technique, allowed us to produce a more complex geometry while not sacrificing structural form. Our robotic hand was then simulated using properties of the chosen materials in order to evaluate the dynamics of the system. These results were then used as an input into our motor selection.
The electrical subteam is responsible for motor control, data collection, and communications. There are 3 main systems that accomplish these tasks: Rover electrical hardware, Rover software, and base station software. The interface method between the electrical box and the Rover's hardware has several key features that set this year's Rover apart.
The system is modular because we are able to easily insert and remove the box from the rover. We thought this was an important goal because on the Martian surface, an astronaut would need to be able to efficiently and quickly remove the box, diagnose problems, and reinsert it. This is accomplished through the use of Anderson power pole connectors inside weatherproof housing, which will provide an efficient and effective seal with the box and keep dust and other particles out.
The Rover software and the base station software were both designed with configurability in mind. On the base station, we have the ability to dynamically change which controllers are corresponding to which actions. In addition, we can have as many controllers as we wish. The combination of these 2 features allows us to have multiple operators, each with their controller of preference.
Much like the Mars Global Surveyor and the Mars Reconnaissance Orbiter have provided vital data for the Mars rover missions, our team has also used indirect means to plan our competition and find the best use of our time. We've used satellite imagery and also databases from surveys of the area to create maps through GIS software that give soil properties like hydraulic conductivity, porosity, and water retention. And we've also created geological maps and also topographic maps to help us navigate the competition. Together, we've used this data and synthesized it to find a number of sites. The sites selected all contain recent erosional features. These features not only indicate the recent presence of water, but are also favorable for our auger-based instrumentation. Whether you're on Earth or Mars, water leaves distinctive signs that are there to interpret. Teams that are best able to interpret these signs can build the best cases for water in that location and can also build the most compelling cases for life as well.
With this design, current demonstrated capabilities, and strategy going forward, we are confident in our ability to perform well in the 2016 University Rover Challenge. And on behalf of the Michigan Mars Rover team, I would like to thank you for your consideration.